Preamp on. Scope on. Micronta power supply on. Circuit is set up. Diagrams made. Cat's on the bench. Ready for the next video. Well, greetings everyone. Today I'm messing around with an experimental amplifier design. At least it's experimental to me. It's been used since the 70s, but I want to look into it again. If you watch my channel, back in 2013, I set up a circuit where I had an operational amplifier driving into an unbiased output stage. And you can see this stage, you can't bias it the way it's set up. The emitters are connected together and the bases are connected together. So there's no way to bias the circuit to have a continuous current flowing through it so that there's no crossover distortion. See, the problem is, no matter what voltage you put on this base, the exact same voltage is going to appear on this base because you can see they're tied together. So in order to turn this transistor on, I'd have to have more than 650 millivolts put on this base relative to this output node. And in doing that, you couldn't turn this transistor on because it would need 1300 volts less to turn this on. And the converse is true. If you put negative 650 millivolts on this base, then you'd be 1300 millivolts too low to turn this transistor on. So there's no way to bias this circuit. And if you play music to it, there's always going to be that dead zone where the signal would have to be more than 650 millivolts in the positive and 650 millivolts in the negative side before these transistors could work and put any sound out. And when I demonstrated it with music, it sounded really hideous. And in doing that, I had the feedback from this operational amplifier connected at its output. So next I moved the negative feedback point to the output of the amplifier, encasing this output stage in the negative feedback loop. And it was pretty surprising. It made the amplifier actually sound halfway decent, but it still had a lot of issues. Because what was happening was this amplifier was slewing very fast to cover over that dead zone. However, it didn't do it perfectly because you could hear some noise in the music still. It sounded like dithering to me, like if you had a low bitrate digital audio signal, maybe like 8 bits or so, and you're playing music, you can kind of hear that dithering effect. That's kind of what that sounded like. What I did is I connected that amplifier to my computer and recorded music directly into the video for people to hear it. I actually listened to that video to be sure that the YouTube algorithms wasn't smoothing that over or whatever. But I could clearly hear that, even though some people said they didn't notice it. But to me, it stuck out like a sore thumb. So yeah, that circuit didn't work all that well. However, at the time, I didn't know that I was one step away from what's called a current dumping amplifier. What's done in that case, in the most simplest form, is a resistor is connected from this point to this point. And what happens is it feeds forward current from the previous stage here and bypasses the output transistors. So when these are not operating in that dead zone, it's actually sending current through and allowing the speaker to play that part of the signal when these transistors are turned off. And because negative feedback is still encompassing the entire amplifier, it will clear up any of these irregularities and make it sound pretty good. And that's the idea anyway. Now, this current dumping technique comes from an amplifier that was designed in the 1970s. It's from England. It's called the Quad 405, if I'm remembering the model number correctly. Its design was a lot more complex than what you're seeing here, but the idea was the same. It relied on inductors and resistors and capacitors to reduce the effects of that crossover distortion, that dead zone. It also had a high-performance, high-speed Class A amplifier up front that had a lot of bandwidth, so negative feedback could do its job. See, the negative feedback requires very high open-loop gain, and of course plenty of gain within the audio spectrum for it to do its business to clean up any nonlinearities. So that Quad 405 amplifier had a lot of fans, but as it was, it was a very good amplifier. It did its job. A few years later, I believe it was a couple of college professors published a paper on the current dumping design and pretty much proved how that circuit could produce very low distortions across the audio band. So it is, to me at least, a valid technique to make an amplifier. So what I want to do is, in its simpler form here, is kind of play around with it and see what it sounds like. Okay, so I have a circuit set up here with an NE5534, just a single op-amp IC that's behind that capacitor there. Now this schematic is very simple. I'm not showing the bypass capacitors or anything like that. I'll furnish a more complete schematic at the end of the video. Have the two output transistors here. These are just supply bypass capacitors, and for the op-amp there's some ceramic bypass capacitors. And yes, I know somebody's going to say it, that using one of these socket boards is not ideal. I know that. You don't have to make a comment. It's just that to monkey around and change the circuit, I'd have to solder and unsolder and do all that just to make this video. I'm not going to go to that extent. Hopefully I get reasonable results as the circuit is here on the socket board. Okay, so now I'm feeding in a 1 kilohertz signal to the amplifier, and let me crank that up a little bit. You see it clips on the bottom. That's because of the op-amp. I don't know why. I might try a different op-amp. But the 5534 is clipping on the bottom rail. I'm using plus and minus 6 volts supply. I think the LM4562 is much more symmetrical in that regard. But anyhow, so I have this output signal, and you can see there's this dead zone. I can zoom in on it a bit more. You can see a dead zone here where the transistors are turned off. So, if you have a really low signal, like if I turn this down, turn that up a bit, you can see that becomes really bad. In fact, due to the asymmetry, we lose the top part. So I'll turn that back up. So if I didn't mention it before, I'm taking feedback from the output of the op-amp. So the push-pull output stage that is not biased is not within the feedback loop. So you're seeing all this distortion. Okay, so let me adjust the circuit so that the feedback loop is encompassing the output stage. Well, it wouldn't be right if I didn't play you a sample of music with the amplifier in this state. So here goes. Sounds pretty good to me. I don't know what it sounds like to you, but that's great. No, it sounds pretty awful. So now I've moved the negative feedback takeoff point to encompass the entire amplifier. And as you can see, it looks much better. See if I can turn this up. There's a little bit of noise getting in. That's not anything to do with it. I think I can see a little notch there though. Oh yeah, there's still a little bit of a notch there. Let's turn this back down. Yeah, let's play a music sample and see what that sounds like. This is copyrighted music, so I have to be careful. Statues melt from moldy light. Well, I played a lot of different music off camera, just, to carefully listen to it. I'll be damned if I can't really hear any issues with this. It sounds pretty good. I'm not even to the current pump stage yet. I know my ears are pretty decent. I've been evaluating audio for a while. The biggest difference of audio to me is listening room speakers and source material, but this thing is amazing. Well, I'm going to pursue with the feed forward resistor here and see how it affects the sound. Well, I don't know what happened here. Everything was great. Now it's this. I tried a different chip. I thought I blew up the op amp, but same thing. So I don't know what happened. I gotta play around and see what broke on this thing. Maybe I popped the transistor. When I was flipping wires around, I could have shorted a transistor or something. Well, stand by. Okay, I think I got the problem sorted. I had the output wire here connected to the emitters instead of the base of these transistors. Kind of tight in there. I don't have the luxury on these socket boards. You got to keep everything tight and tidy. You can't run wires everywhere, or you'll run into problems with more distortion and oscillation and stuff like that. But that actually threw me for a few minutes. Looking around, I changed the op amp and it was behaving the same. So okay, anyway, back on track here. I'll just leave these mistakes in the video because I'm not perfect. Okay, barring any bumbling errors, we'll continue on with the experiment. Okay, so now I have the amplifier set up so the output, or the feedback, is now on the output of the op amp. And I'm going to add this resistor. And since I now put the feedback on the output of the amplifier, we're seeing the distortion again, the crossover. So I'll put the 22 ohm resistor right here. Put that into the circuit and see what happens. Not sure what to call that. Maybe the feed forward resistor. Okay, so that cleared up the distortion. Got some clipping. Like I said, I might try a different op amp. Maybe not in this video though. Looks like it might be oscillating. I think that's just the way I have the... Oops. No, it's fine. I just have the scope set on peak detect because I don't get any bogeys in the FFT, so I leave it in peak detect mode. I have a 100 ohm load on the output now. I'm going to see what happens if I put a 4 ohm load. Actually 3.9 ohm resistor. So we're seeing the crossover again, but if you look at it closely, it is not straight across. It's now at an angle. So I think that would be an easier slew rate for the amplifier's feedback to correct if I put the feedback back on the output. So I'll try that and we'll see what happens there. Okay, let's see what it looks like now. Let's turn this up. Don't see any sort of notch or anything. Looks pretty good. Okay, I have a 4 ohm load on the output. 4 ohm caused the output to sag somewhat. Let's see. Yep, we don't get all the way to clipping. But I can tell putting that on there, it's got very good damping characteristics because the whole sine wave does not shrink. If I turn it out of clipping, and let's take a look at the distortion. This is the 1 kilohertz fundamental, 4.5 kilohertz pilot signal, and there's no distortion bumps at all. It's clean. Let's try some other frequencies. Okay, we're at 10 kilohertz. You can see there are some bumps at each multiple frequency, so yeah, there is some high order harmonics going on. Now we're at 20 hertz, and there's really nothing. There's no pilot signal at those other frequencies because I don't have files made with pilot signals at those levels. Well, I'm back on the 10 kilohertz waveform again, and here is the source of the distortion. You can tell it's a very sharp little bump, so it's going to cause high order harmonics. And yeah, I think what's happening, the op amp here is not able to supply enough current. So I'm going to try lightening the load. I'll switch to an 8 ohm load and see if it does any better. Okay, I have the 8 ohm load on. If I disconnect the load, you see the distortion nodes go away. But when I connect it, it certainly comes back. So let's turn that off. It's much better. It's still see a little notch. These little operational amplifiers, they're not good for a lot of output, maybe 25, 30 milliamps. In that dead zone where the transistors are off, let's see, 0.65 volts divided by, we'll say 8 ohms. Yeah, I'm still going to need about 81 milliamps. So if I had a stronger operational amplifier, one with more output, plus, you know, it still maintained a decent bandwidth and open loop distortion, I think we'd have a pretty clean waveform, showing you that the little amplifier here can do the business. You know, the distortion is not, it's not awful. You know, 1% would be up here, so these are little nubs of distortion. Not what I would call hi-fi by any measure. I think it's important to include this part here to show what's happening within the amplifier circuit. So what I've done is set the feedback so that the output stage is enclosed in the feedback loop. Now I'm scoping at the output of the op amp. So what you're seeing is the signal that's being sent to the output stage to correct its crossover distortion. So what's happening here, it's slewing very fast to, you know, cross over that dead zone in the output stage and give you a nice sine wave on the output. I can understand why people would have reservations against this type of amplifier design, because you are leaning heavily on negative feedback to correct this. Now, of course, this is not set up like, for example, the Quad 405. This is a worst case scenario where I'm allowing negative feedback to correct the crossover distortion. I'm not feeding any signal forward. So what I'll do now is I'll put in the feed forward resistor and we'll take a look at it again. Okay, so now I plugged in the feed forward resistor, you know, that 22 ohm resistor that goes from the base to the emitters to send some of the signal from the op amp directly to the output. And again, we're getting a nice clean sine wave. So you see how that feed forward concept reduces some of the dependence on negative feedback. However, I only have a 100 ohm load on the amplifier right now. So let me put a 4 ohm load and see what happens here. Well, you can see it comes back. And again, part of the problem is I'm using an op amp that can't deliver enough current directly to the output with a 4 ohm load. So that's part of the reason it does that. But again, I wanted to demonstrate what's going on with the negative feedback and the corrective signal that's being sent to the output to correct the crossover distortion. I also figured out why I'm getting so much offset. I thought I could get away with it, but here's what happened. Well, at idle I measured the output of this amp, and it's offset by almost 400 millivolts. Well, what I did is I made this circuit simple. I did not include a capacitor here. What that does is make the DC gain of this amplifier 1. And even with DC flowing through this part of the circuit, you still have the voltage divider effect on the DC, and this will amplify DC. But when you put a capacitor here, it blocks DC, so DC only sees this loop here, and it makes the gain 1 for DC. I do have a little bit of output offset that's being amplified and made greater. The amplifier has offset null pins. I could correct that, and I could put that capacitor in there, but you know, at this point I'm not going to bother with it. Just important to understand what's going on and, you know, figure out the little problems with these circuits. Well, I searched YouTube's audio library for some piano music. I have a lot of it, but I'm just afraid that it'll trigger the copyright match content worm, or whatever the hell it's called. And I don't want to risk that, so I just downloaded something I know I could use. So I moved the operation over here, connected this lead, plugged it into the computer, line input down behind there, the old computer right there, and just play in there and record it into Audacity. I got the level set and everything. That way I can give you an exact copy, well, as close as I can, to what the music sounds like. Piano music is very good, I think, for this test. You can really hear the higher level distortions. You can't really hear it with rock music when you have, you know, guitars that are already distorted. So playing it with music that has more clean tones, I guess you could say, you can hear that type of thing. So I'll go ahead and do this and play back the music in the video, and then come back at the end with the schematic. Okay, here is the schematic. I think I have everything on there. I drew it up at rapid speed. And there's not really much to the circuit, to be honest with you. It's pretty basic, really. The op amp and a couple transistors and a resistor. I put the power rails in with the decoupling caps and the output Bouguereau or Bouguereau cell, however you pronounce that. Some people call it a Zobel, but technically it's more accurately a Bouguereau cell. Supply voltage was kind of random. It's just whatever was set on the supply. You know, I set it around 6 volts and that's what it came out. I didn't want to set it too high because at a higher voltage the output swings more into the load, meaning more current is required, and at some point the gain starts drooping on the transistors, and you know, I'm not sure the little op amp IC would have enough current to drive those. Output power is about 1 watt into 4 ohm loads, and again at these supply voltages. But I think I could do a lot better if it clipped symmetrically, and one with an op amp that had a little more current might have gotten better output power. So I thought this was a pretty interesting little amplifier to tinker with and experiment and see what I could get out of it. Pretty happy with the results. I'd like to see lower distortion, though it wasn't excessive, but at high frequencies there was still some distortions, but definitely not what I would call hi-fi. Perhaps I'll pursue this in another video and maybe expand upon it and make it better, make it something people might want to build. I might want to try finding a op amp with more output. That's the key, I think, to making this work. But we'll leave it at that, and thanks again everybody for watching. You know, you got to experiment, make mistakes, fix those mistakes, and go on.